Good morning. Welcome to our talk over the AirTag Shenanigans with the most over-engineered Keyfinder. In theory, we are 3 presenters, but one got lost. And so my name is Thomas Roth, aka Stack Smashing. Over here, we have Jiska of wireless security fame, and Fabian, who hopefully will be back soon, who is an independent security researcher. And we basically looked at the AirTags. Now, before we start, there are a couple of people that we need to thank. So first off, Colin O'Flynn, who for me was the person that nerd-sniped me with the AirTags in the first place. Leonard Wouters, with whom we did a lot of reverse engineering. David Halton, who, as you see, did some awesome PCB layer stuff. Limited results, because we are using one of his vulnerabilities. And also Doc Kruse, who helped out. And so check out these awesome people. They're really great. Now, let's talk about the AirTag. Now, the AirTag is on the surface a simple key finder, and so really not interesting. But the reason we are saying it's over-engineered is because it's like if you give an engineer unlimited budget and tell him to design a key finder, this is probably what he will come up with. And so the AirTag contains the U1 chip, which is an ultra-wideband chip, and so you can precisely locate it using a modern iPhone. And it also, instead of just using Bluetooth with one device or so, it uses the Find My network. And so each iPhone that walks past the AirTag will transmit the location of the AirTag up into the cloud so that you can track it via any iPhone, basically. Also, kind of funny, it's a key finder, but doesn't actually attach to a key without further accessories. Anyway, so when I heard about the AirTags, I wasn't interested in them at all because, it's a key finder, so why bother? And then I woke up and I got a message on Twitter saying, hey, here are the flash contents of the AirTags. And so somebody dumped the spy flash of the AirTags. And obviously, being a hardware hacker, if I find a firmware dump, I have to look into it. And so I hex dumped it and immediately recognized these patterns. So this is the basic pattern of an RTKit firmware, and RTKit is the embedded real-time operating system that Apple uses on all their tiny devices, basically. And this turned out later on to be the firmware of the U1, so the firmware of the ultra-wideband chip, which so far was only in like the iPhone and other expensive devices, but now we have it in a very cheap device, which is interesting to us, given that ultra-wideband is still a pretty new technology. Furthermore, we also see, if we just run strings on this, that there are references to the NRF52 SDK. And so in the AirTag, they apparently use the standard NRF SDK. Your iPad just died. And so if you open up an AirTag, which, by the way, is not as simple as it should be, so you have to be really careful. It breaks very easily. It has a very thin PCB. If you go into an AirTag, you will see this, which basically is just the backside. And there's not much of interest here, but what you might notice is that Apple was nice enough to give us a ton of test pins. And so if you open it up, there's a ton of stuff to probe, and that's really nice. Interestingly enough, Colin was the first one who really looked into this, and he created what's basically the default AirTag pinout. And so now, if you see any publication on the AirTags, we use this numbering scheme. And so if you ever see, hey, spy flash is connected on pin 29 or so, this is what they refer to. So it's basically the standard AirTag numbering system. Otherwise, on the backside, there's not really anything interesting. There are only passives, except that on the bottom right, we have a small accelerometer. And that's basically it. Otherwise, it's pretty boring, let's say. Now, if we manage to remove the PCB, which, by the way, is really difficult because it's glued in, it's super thin, you will break it. It's best to just not do it because there's nothing interesting from the hacker side on there, but it's interesting from the hardware side. And so what we see here is, first off, this big silver chip. This is the U1 chip, the ultra-wideband chip of the AirTag. And what's really cool is that they actually populated an antenna connector, and so you can directly feed into the AirTag from your SDR. And so it's really, really, really nice if you want to do a couple of experiments. Otherwise, we have a small spy flash, which, as you will see, is not really interesting. And then we have the NRF52832. This chip is basically found on any key finder on the planet. Like if you open up a Samsung key finder, it probably contains more or less the same chip. Now, the NRF52 on the AirTag handles the Bluetooth communication, the iPhone communication. It handles NFC, and so if you touch the AirTag with an NFC-capable phone, it will bring up a URL. And it's also known to be vulnerable. And so basically, on the backside of the AirTag, we have the programming interface exposed. And if we connect a programmer to it, unfortunately, it's locked. And so this locking mechanism on the NF52 is called App Protect. Basically, it allows you to, when you ship a device, you lock down the debugging interfaces, and this will ensure that nobody can dump your firmware in theory. You can still erase the firmware, you can still flash a new one, but you can't dump the current one. Luckily for us, there's a way to bypass this App Protect. And so last year, Limited Results published an NF52 debug resurrection. And so he basically managed to use fault injection to re-enable the debug port, which then allows us to dump the firmware. And so the plan for me, having just acquired a couple of AirTags and already broken 2, but that doesn't matter, was to basically find the test pins for the SWD programmer, find whatever power supplies we need, glitch it, and then hopefully dump the firmware. Now, glitching is for a lot of people very magic, but it's really very easy. All we are doing is basically we interrupt the voltage towards the chip for a couple of nanoseconds, maybe microseconds, and this will cause different corruptions in the chip. And so if you time it very precisely, you might be able to skip instructions, you might be able to corrupt register contents, and so on and so forth. And if you think about the boot process of this processor, at one point, the chip will check whether the debugging hardware has been disabled or not. And if it's been disabled, it will skip the step of enabling the debug hardware. However, if we manage to find the time of this check and we interrupt the power supply at just the right time, we might be able to trick the chip into skipping the check and jumping into the enable debug hardware procedure. Now, this is not as easy always as it sounds, because a big issue is that basically a processor on the outside, mostly for microcontrollers, has a single power supply. So for example, the NF52 runs on 1.8 volts. However, inside of the chip, we generate different voltages for different peripherals. And so for example, the CPU core will run at a much lower voltage than your Bluetooth core, and so on and so forth. And the issue is, we really want to target the CPU core. We don't really want to glitch anything else. And so how do we get access to that voltage rail without decapping the chip? Well, it turns out that regulators are very noisy. And to make them less noisy, chip designers give you a pin to add an external bypass capacitor to basically smooth out the ripples. And this gives us direct access to the internal CPU rail of the CPU core. And so if we attach a switch to ground to this, and we close the switch, we will interrupt the power to the CPU core. And if we open it, it will be restored. Now, obviously, it's very difficult to, press a button for 100 nanoseconds at exactly the right time. So instead of a switch, we just use a regular MOSFET. And instead of, our fingers, we simply use a device that does very precise timings. Now, normally you would use like a chip whisperer or an FPGA or so, but I always like to hack things the cheapest way possible. And so with the Raspberry Pi Pico, you can glitch the AirTag with like $4 of equipment. And I think that's pretty neat. And so basically, if we toggle this I/O high, we will enable a MOSFET, cut the power to the CPU. And if we toggle it low, it will go back again. Sounds simple enough, but how do we do this on the AirTag? So first off, we are very lucky that the bypass capacitor is on the easily accessible backside of the AirTag. And even nicer, Apple gave us a glitching test pin. And so all we have to do is solder a wire onto this, and we get direct access to the CPU core voltage. Yay. And so we hook this up using a very cheap MOSFET, literally 20 cents of equipment. And then we want to measure when we turn on the AirTag, when does it start booting? Because we want to glitch at the time offset to the time of boot. And so to measure that, we basically measure the regulated power supply of the NF52. So as soon as that goes high, that's our trigger signal. We wait a couple of microseconds, glitch, and then hopefully re-enable debugging. To power cycle the AirTag, this is probably not spec compliant, but we simply can power it from a random I/O. Like this works totally fine. And then we just hook up an SWD programmer. And so that's basically all our setup. And the way this works is if we start from scratch, we turn on the AirTag by giving it power. Then we wait for the NF52 power supply to come up. Then we wait whatever our delay is. We enable the MOSFET for a couple of microseconds, and that will interrupt the power, and then we restore it. And then we check with our SWD programmer whether we can access the chip or not. That's literally it. And in real life, it looks somewhat like this. So we have our AirTag. This is really messy, but this is the first one that I actually glitched, and I thought it would be more honest to show the real thing. Then we have a J-Link debugger that I use as the programmer, and then a small breakup board that I built for the Pico that basically has the MOSFET and so on board. And once this is running, we can see on oscilloscope, we have a lot of dithering. Our timing is not very good, but we only have to get lucky once. So we just let this run for like 20 minutes, and eventually, hopefully, we get lucky. And we control this via a small Python script. This is all open source. You can find it at the links at the end. And eventually, it will say success. And then we have the firmware. We have the flash contents. We have all the internal CPU registers, and so on and so forth. And we can start analyzing it. Now, what I always like to do is to just run strings on any firmware that I get, like just to see what's inside, what can I immediately tell. In this case, there are a lot of interesting things. There's, for example, a core crypto reference, which is the Apple cryptography framework. There's an interesting link, and this link looks very similar to the one that when you touch the AirTag with NFC, this is the link that you will get back. So that's apparently in the NRF firmware. And so that means we can fiddle with it. And having something very easy that we can fiddle with and test whether we modified something is really cool because it allows us to check whether we can modify the firmware. And so I basically changed the URL, flashed the AirTag, and now if you scan the AirTag, what else are you going to do, right? Other cool things in the firmware, the serial number is in the firmware and you can actually adjust this. It's not checked. And so you can literally pair any serial with iCloud. And so my serial number is stack smashing. And there's a couple of other interesting things in there, such as your censored email address and so on. Now, what was curious to us is, can we clone an AirTag? Is there anything that prevents us from, is the U1 maybe used as a secret element, or is it really just the NF52? And so what we did is I dumped my AirTag, sent my firmware over to Leonard. Leonard flashed his AirTag, and we checked what would happen if we have two clones at the same time online. And so my AirTag was nicely located at my home. And then Leonard enabled his, flashed his, and suddenly my AirTag was somewhere in Belgium, a couple of 100 kilometers away. And so we can trivially clone the AirTag. And even what's interesting is that if you, let's say you find a stolen AirTag, you can reflash it and reuse it as your own. Like there's nothing that prevents you from doing this. Also on the hardware side, David Halton has this awesome, very precise polishing machine, and he basically delayered the entire PCB. And then I went ahead and combined all those pictures in GIMP, and so we now have like full, very high resolution pictures of the entire PCB, and so we can just trace any connection. And this is all online, so if you want to, draw a couple of traces, feel free to do so. And yeah, that's basically the hardware side we built. And with the hardware side all done, it was time to team up with some people who do software. And yeah, let's talk about firmware.
So what are we actually looking for in the firmware? So first of all, there is a lot of stuff that's Bluetooth specification compliant, so handlers for pairing, and just handling packet data. There's nothing AirTag specific in there, but the cool part here is that we can look it up in the specification, so it's easier to find. And then there is the part that we are really interested in, which is everything that Apple built for the AirTag. So, for example, playing sounds, updating the firmware, and so on. To understand the following slides, you need to know that a Bluetooth packet has, first of all, some physical layer stuff. So ACL or LEU is just a physical transport layer, so to say, so the lowest layer. Then we have L2CAP, and L2CAP is for fragmentation and raw data transfer. So Apple is using this, and optionally you can have GATT on top. Apple is also using this one. So we are dealing with L2CAP and GATT in the following.
So let's talk about what this looks like in firmware. In the NRF52, we have something called the soft device. It's basically something like a small kernel. The software that's implemented on top of that talks to the soft device using supervisor calls and gets notifications through IRQs and events. And that's how you implement custom Bluetooth firmware on top of it. This is the memory map, or somewhat like the memory map for the NRF52. The soft device is a big binary blob that is located right at the beginning of memory. This is the big binary blob that's shipped by Nordic. You flash it there, and then you put your custom code underneath it. Then farther up in the memory map, we have RAM, and then similar to other ARM chips, there's some MMIO peripherals. So when we're starting at reversing something like this, it's really useful to understand what well-defined interfaces there are, because these are things that you can cross-reference, that you can understand, and that you can start out with. In this case, it's the interface between the soft device and the custom app firmware, and the interface between the MMIO and also the custom code. So let's start looking at the supervisor calls. We can find a list of all of the supervisor calls in the firmware. Here I've already given a few of those names. When you're starting out, they will not have names yet. So this is what we're trying to do. Let's, for example, take this one here, which is supervisor call A8. Turns out if you check in the SDK, which is a library of header files and custom code provided by Nordic to talk to this soft device, we can find some constants that say what is what, basically. We can see that A8 here is the GATT service add supervisor call. And then farther down, we also find some documentation, what it does, and type information that we can use to understand how data is shipped across the boundary between the app and the soft device. We can propagate that into our disassembler here and add some type information that will help us reverse engineer it and go from there. So there's not just the supervisor calls, but there's also events that happen. That's a bit more complicated. We have to find a function called NRF section iterator init. This is also part of the soft device, or of the SDK, not of the soft device, sorry. Then we find calls to that, and that gets passed a pointer to a big list of handlers. And these handlers will get invoked when there's an event passed by the soft device to the Bluetooth application. So this is the other entry point that's really interesting to start reversing at. So on top of those basic entry points, we can start figuring out what higher level SDK functions are that are in the Nordic SDK. We can figure out accesses to the MMIO region, cross-reference those, and figure out other peripherals, such as UART or TWI. And there's also some functions that don't use the soft device or any external surfaces. These are the most difficult ones to identify, but things like function ID or other signature-based approaches can help here.
So the next part that we are interested in is everything that's Apple-specific. What you can find in every BLE device, or almost all BLE devices, is a GATT service or GATT services with characteristics that you can write to or read from. And some of them can be protected, so only available after pairing. And the important part about those characteristics is there are some that are not that interesting, just like reading a name of the device. But there are also some that Apple defined, for example, for the firmware update, or that are used during a special pairing process. And you can just use this tool that I show here, the NRF Connect, to scroll through them and see what they do, at least like what values they return, and we will now analyze them in detail. So here's one example. If you have the initial pairing, you have a normal BLE pairing, but then on top you have a GATT read and a GATT write. So the read is to get information from the AirTag, like the serial number and so on. And then there is a pairing that involves the iCloud and that creates a certificate that is then written to the AirTag, and this is all done by GATT.
So let's look at what this looks like on the firmware side again. Here you can see part of a very big function. In fact, I can show you. I can show it to you very quickly. Here, so zooming out, you can see there's a long list of basic blocks. Each of these basic blocks here sets up one specific GATT service. Here in the beginning, for example, we have GATT service 8004, which is set here. They all have IDs. And then there's a global variable that says this is basically what's read by the soft device when it's shipping out the data. And there's also some other handlers that can be set. These handlers are invoked in the notify. It's farther down in the call stack from the list of observers earlier that I showed you. And these handlers will get dispatched depending on which characteristic is written to. So we can, by finding these and reverse engineering these, we can figure out what's happening when we write to a specific GATT characteristic.
Now, you need to know this is Apple, so they define everything twice. They have GATT services, which are on top of L2CAP, but they also use plain L2CAP, and some stuff is implemented in both of these, and it just depends a bit on the context, which of the two they are using. So, for example, there are certain AirTag commands. You need a secure connection to the AirTag to use them, and then you can issue a command like, let's play a sound. These commands are then even acknowledged and so on, but this is all not specification compliant. So this is proprietary stuff on top. You can see it is like an L2CAP packet starting with hex 91, indicating it's an AirTag command. Then it has a length field, an operator field. We don't know what these operators are. And then it's followed by data. And we just want to find out what it means and how we can issue them to an AirTag. So the typical approach would be you pair an iPhone and an AirTag, you extract the keys, you sniff all the communication with Apple's packet logger, and then re-implement all of this by hand. So I use my AirTag, I press play sound, and then I check all the commands that are sent and try to send the same commands to the AirTag and see if it also plays a sound. But it still needs the pairing with the iCloud, so you still have some Apple dependencies, and you also don't know the full command list. So if there are like hidden commands never used during the normal AirTag usage. So instead, if we want to get a full list, we need to look into the implementation. On iOS, you have the Bluetooth daemon, which communicates with a Bluetooth chip. And this is where you have true support, for example, with the packet logger and can sniff the packets or even modify the packets if you hook into this with Frida. Then the location daemon is a client. It registers for the AirTags as a peripheral. So the location daemon has the actual implementation for the AirTag and the AirTag protocol. And this is the one that we are now going to look into. The location daemon, at least the part we are interested in, is written in Objective-C. And Objective-C and static reverse engineering is not so great because often there are objects defined in different libraries, and this is not fully resolved if you don't also include them and so on. So it's not so nice for static reverse engineering, but dynamic reverse engineering works very, very, very nice. So let's say if we want to play a sound, then the stuff that's invoked is there's a Durian service. So the code name for the AirTag is Durian, and CL is for call location because we are in location D. This is then invoking a task. This is then issuing a command to the AirTag, and the commands also have the first field, which is the opcode, and we can even resolve this opcode. And we can use Frida trace to just look a bit into this. So here you can see I just play a sound. So we have the Durian service, which plays a sound sequence. And then we also see at the last step this command that is created. So we now know what we want to hook. It's time for Frida and creating our own hooks and modifying commands. So what you can see here, for example, is there is the command that can also have a description. And with Frida, for example, I can now print all the command names and just hook the debug print function, iterate over all opcodes and print them. This print is created on an iPhone 8. It does not have the U1 chip, but you can still see here that we have the rows commands for the U1 chip present, so we get the full list of stuff that's supported on the AirTag, and we can now also issue them.
So in the firmware, there's a receive handler for this stuff. This is the function that has all of the decision-making process depending on what the opcode is that is being sent over L2 cap. Here, for example, we can see opcode OX2A, which happens to be 42, and that is a specific opcode that represents an operation called set wild mode config. That's just something that the phone does to the AirTag sometimes. But it's actually more interesting at the end. At the end of the function, there's two basic blocks that caught our eyes. There's one that calls a function which I've named task queue and queue, and one that says invoke state machine. They sound pretty weird, but so let's figure out what they are. Apple implemented something that is basically a mini operating system, and there's some custom implementations of primitives that are quite useful here. For example, there's a global task queue. You can put work into the task queue, and it will be done in a main loop as soon as possible, but pretty much immediately. When there's nothing to do, the AirTag will go to sleep, and that's what allows it to save a lot of energy and have a long battery life. So let's look at this. For example, here, in one of the characteristic write handlers, which plays a sound when something is written to it, we can see that there's an invoke state machine command that's being enqueued into the task queue. Farther up, and this will be interesting in a moment later, we can see that there's a sound sequence that's being copied here, and the sound sequence is OX104 and OX205, and they're each 4-byte words. Then later in the main function, we can see that there's a task queue do work function that's being called inside the main loop, and then when nothing is happening, then the AirTag will go to sleep. Here, this is this on idle function down here. So this is one form of nonlinear control flow that we'll need to follow along as we look at things. It's the most simple one. It's clear what's being enqueued, and it's clear when things are happening. But there's more nonlinear control flow everywhere around the place here. So figuring out or understanding how to follow along these things is really important to understanding how the AirTag works inside. Another piece of nonlinear control flow are timers. The AirTag uses the timers that are taken pretty much exactly from the NRF SDK's example code. So let's look at some timers. And again, I'll take the playing a sound as an example here. Timers are created using a call to app timer create, which is a function that's in the example code for the NRF. And there's a pointer to a timer structure that's then used when starting a timer or ending a timer. So looking at the cross references, we can see a call to app timer start. We can also see a call to app timer stop. When starting a timer, we also add what the callback handler is that's being called. Now that we know how to follow timers and so on, let's get to the interesting part. What's the state machine thing that we've seen a few times already? So the NRF can do different things in different states it's in. And it needs to keep stack of what's allowed at what point. And it does this by implementing a big state machine. So in the state machine, we have different cases for successful tasks and non-successful tasks. And there's a big dispatch handler, which contains all of the different states that we can be in. And it also contains the handlers for these states. So let's, for example, take the state of playing a sound. There's a list of handlers here, and each command that can be sent to the state machine invokes the specific handler. This is pretty complicated to understand when you're looking at this. It's difficult to see what's happening, where and how things fit together. So we needed to figure out a way to understand this better, and I've written a small script that will parse the state handler table and then print out some graphist dot representation of it. Then running this, we get a somewhat complicated graph of what's happening, but and then using the method of intent staring at things, we can start adding labels to things and understand what they are. For example, here we can see this, there's one state that's associated with playing a sound and other states that, other transitions that can happen, and we can see from which states we can go to playing a sound and not. Or when the AirTag, for example, will unpair.
So now we have two parts of research that we can put together. There is my part with all the dynamic FreeDA instrumentation from an iPhone, and I can run tasks and commands. And then there is Fabian's part with the static analysis to figure out implementation details. So I can run commands and he can figure out what the parameters are exactly. And here's one example. So this is some instrumentation for the AirTag that I also put on GitHub like half an hour ago. And there is the opcodes that you can see. There's also the task initialization that you can see. And in the bottom, I have the play sound sequence command. And you can see there is multiple sound sequences. So like the 205 that you saw, the 1 is selecting the first sound sequence. The 3 means I repeat it 3 times. The 23 is just an offset into the sound. And the 1 is the length of a pause. And then the next 4 bytes are the next part of the sound sequence. So I hope that you can hear this a bit when it plays. So this is just the instrumentation that we can do, but of course also for all the other commands and opcodes. The next part is the firmware downgrade. So it's not just about having fun with the one or the other opcode and playing sound, but really do something useful with the firmware for experimentation. Usually the iPhone checks for updates every 2 hours and 30 minutes. That's a bit long to wait, so I want to trigger an update manually and then also re-instrument it for a downgrade. So I just pair my AirTag again, and then after exactly 5 minutes, there is a check if there is an update available. So the search party daemon just tells the firmware update daemon, hey, try to update. Then the firmware update daemon just invokes the Durian updater service and says, hey, do an update for AirTags. This is then querying the search party daemon, and here I have to fake the beacon list. So I have to fake the information of my AirTag and just say with FreeDA, yes, this AirTag is outdated no matter what, so that we can trigger an update. Then the Durian updater service contacts the mobile asset daemon and says, hey, download a firmware. It just downloads it, or if it's already downloaded, it's also okay, and then it's unpacking and validating it locally. Now there's an interesting part because now the U1 chip is involved. The U1 chip in each AirTag has a unique ECID, and during the update process, the AirTag U1 chip even creates a nonce, and this nonce is only used once, so the update will only be accepted if the signature that's then created later on matches the nonce. This is called personalization information, but it's really just for the U1 chip. It's nothing linked to your iCloud account. This takes 15 seconds, which makes it a bit easier. So this whole timing here enables us to replace files on the file system of the unpacked update. Then this personalization information, along with the checksum of the U1 firmware, is sent to Apple's touch-to signing server. So this one checks if this is U1 firmware that's allowed to be signed and flashed to a U1 chip, and also adds the personalization information to a signature, and then the U1 firmware is repacked with this ticket from the TSS server. And then finally, the firmware update is invoked, including the stuff of the NRF firmware, and this is then being sent over BLE, which takes another 2 or 3 minutes. So this is the really interesting part of how to either do an update or also a downgrade if we replace this. We can always downgrade the U1 firmware to a version that is still TSS signed. So if Apple signs it, we can downgrade U1 even to a non-matching NRF firmware. And the NRF firmware itself is not tied to anything special on the AirTag, so we can always downgrade to any NRF firmware that has been released. The firmware format is interesting to understand. I also have a script for unpacking this because it has 3 parts for the NRF, the Bluetooth application, the soft device, and the bootloader, including their signatures. And then we have a special FTAP file with the U1 firmware, which is not yet signed, so this is the unsigned version of it.
So again, let's look at how this is implemented in the firmware. There's a get-receive handler for the characteristic number 6001, which is the one that receives all of the data that's being pushed over Bluetooth LE with all of the firmware packets. And we can see that there's a big switch case here for the different images that we've seen earlier. For example, the soft device, the Bluetooth app, and so on. The interesting part here is that there's a signature check that's being done on most of these images, especially, well, the NRF ones. And this signature check is implemented using SHA-256 and ECC with group P256. Then, for example, for the U1, there's no such check because the U1 verifies its signature on itself. There's also a handler that handles the end of the transmission, and that's handler 6003. And that has different handlers depending what the chip should do after receiving this specific image, whether it, for example, should reboot into the firmware and into the bootloader and start the new firmware, which ends up happening here. So you can see these characteristic write handlers are really crucial at understanding the interface to the rest.
Yeah, so what does this all matter? Well, first off, AirTags are a really fun target. They are relatively cheap. They have a lot of very modern features. You have the U1, UWB, you have all the interfacing with the iPhone and so on. And I mean, it's an Apple IoT device, so it's interesting from the get-go, for me at least. What was really interesting to me was like the requirement of almost having full stack researchers for this, because you have the iOS side, you have the Bluetooth side, which I have no clue about. You have all the static analysis that you need to do. And so then the hardware side, obviously. And so, yeah, in the end, we are able to, glitch open any AirTag. We are able to play sounds on any AirTag. We can play the unauthorized sound, I guess, on any AirTag. So if you want to troll a room full of people with AirTags, you could do that. And yeah, it's just also a great base for U1 and ultra-wideband research. Because as I said, so far, any ultra-wideband device cost a couple of $100s. Now it costs, I think, $30 or $40. Also, glitching is fun. It's really not difficult. You can find all the source code, documentation, and so on and so forth on these GitHub links that we'll also post on Twitter. And so if you want to glitch it, just buy a Pico and a MOSFET. If you want to take a look at the hardware, we have that online. We have all the scripts for Frida and so on online. And yeah, with that, thank you for coming and hope you enjoyed this. And if there are any questions, please go ahead.